All right, synthesis, pause. So when we think about synthesis, I like integrating this into each of our chapters. There is a separate chapter in your textbook. It's chapter 11. We have been integrating synthesis now with every chapter itself. So we won't be isolating chapter 11 as an actual chapter, but just know you have actually learned it integrated throughout now chapter 8, and here we are in chapter 9. And I really want to take this time again to just remind us of how to do a retrosynthetic action. We're going to practice a little bit today. I popped our two questions that we want to always be able to ask ourselves. Did the number of carbons change? Did the functional group change? This will help us identify what's going on, and then we always want to ask ourselves, how did I make that? So let's look at this one. 1, 2, 3, 4, 5, 6 in the reactant. 1, 2, 3, 4, 5, 6 in the product. So the number of carbons in this first example did not change, but we do see that there's functionality that has changed specifically between carbons 3 and 4. It was a carbon-carbon triple bond, and now it is a vicinal dihalide where the two bromines are next to each other. Now, we don't really know how to add bromine syn addition, but we do know how to add them anti-addition. So the first thing that I want to be able to do here is think about rotating around this bond. Let's just rotate to view this molecule, this product, in a different way. And the only reason why I'm doing that is to make myself have a little bit easier time. I do know how to add anti-addition. Halogenation of an alkene is one way to add a vicinal dihalide. So looking at this product, these are the two same, right? These are identical. All I did was rotate so that I could view the product in a different way, view the product better. Now let's think about, okay, if I wanted to do retro analysis, what alkene did I use to add these two halogens anti to each other? I must have chosen this alkene, where it's a cis conformation. That way, when the bromines add, they add anti to each other. Well, that makes life a little bit easier. How do I make a cis alkene? H2 and Lindlar's catalyst. You can just call it Lindlar's. So the reagents that would be required over this reaction arrow for our final answer. 1, use H2 and Lindlar's, followed up with Br2. And that would get you your final product. Now, it's really important that we can visualize each individual reaction to get the overall synthetic picture. So don't be afraid to take chances, make mistakes, redraw things, and always double check with your forward reaction, right? Double check to make sure that using H2 and Lindlar's would make a cis alkene, and then adding Br2 would make that final product where we have the specific conformations of the bromines. All right? Let's do this again. 1, 2 carbons. Well, 1, 2, 3, 4. Yikes. Now we see that, well, we don't have the right number of carbons. I'm going to try one thing with numbering here. Numbering to just count up the carbons. I know I'm adding carbons here because my product has 4 carbons and my reactant only has 2. Noticing that we know how to add on carbons to the triple bond. A terminal alkyne is acidic, and therefore we can use the alkylide ion in order to be a nucleophile and add in an SN2 fashion onto an alpha carbon. But I really want to be able to understand that that functional group of the triple bond would still be there. So I'm going to count this way so that we can see where carbon 1 and 2 could potentially still be. And the reason for that is I still not only add carbons, but also make an aldehyde. And the best way that we know how to make an aldehyde on the less substituted position on a terminal end is hydroboration oxidation. That's where I'm going to start. I want to think backwards. And so the best thing to think about as the last step is using a large boron reagent in THF. You can say 9BBN, you could say a diacylborane, you could just say HBr2. That's acceptable. Followed by the oxidation, peroxide, and NaOH. Now, what would that triple bond look like? Well, it would be a triple bond between carbons 1 and 2 with extra carbons 3 and 4. Getting closer to my reactant. Let's take a step back. We know that we could add that triple bond as an alkylide ion. Let's put it right here. Oops. If we reacted it with an alkyl halide. Carbon 1, 2, 3, 4. That SN2 reaction with our new alkylide nucleophile, the carbon that's sp hybridized with a negative charge. How do I make that? Throw in a reactive base. Sodium amide is great. Sodium amide would be the first step to deprotonate that terminal alkyne. And then we would add in alkyl halide with those 2 extra carbons, followed up with hydroboration oxidation as 2 separate steps. So 4 steps total for this one. Make sure hydroboration oxidation occurs in steps 3 and 4, right? 2 separate steps for those. All right, last one. Again, looking at our functional group changes, we see that, but let's go ahead and count 1, 2, 3, 4. 1, 2, 3. Removing electrons. Ooh, thinking about the best way to eliminate a carbon or to remove a carbon was ozonolysis. So removing carbons was with ozonolysis. Now what we see here is that we end up with an extremely oxidized carbon, has a carboxylic acid. So thinking backwards, the only way ozone made a carboxylic acid was with a triple bond. 1, 2, 3, 4. The other byproduct here would be carbon dioxide that would bubble out of solution. So now we're a little bit closer. We have to be able to say, well, how do we change carbons 3 and 4 from an alkyl halide on carbon 4 to a triple bond? Well, I know how to make a triple bond. It's either with a vicinal dihalide or a geminal dihalide. The geminal dihalide is probably not the best option here. And the reason for that is the only way that we really made them was with a triple bond. Well, we know we don't start with a triple bond, but we do know that we could do this reaction, right, to make that terminal alkyne by doing a double elimination. Because it's a terminal alkyne, we do need a water workup afterwards so that we can put that terminal proton right back on. Let's keep stepping back. How do we make vicinal dihalides? It's with Br2 and a double bond. Keep my counting. And then our last step, how do we make an alkyne or an alkane into an alkene? Is with a base, an E2 mechanism. So a few more steps here. Thinking about overall, we need an E2 reaction to make our alkene. Then we add 2 bromines onto that alkene, so we have 2 leaving groups. We can take that alkene and make it a triple bond. Terminal alkene, or alkyne, so you need to, in the double elimination, reprotonate. And then final step, ozonolysis. Chop that triple bond up and make it a carboxylic acid. Thank you so much. What's really important here is to make sure that we are identifying each individual step. Practice with the individual forward reactions first, and then we can tackle synthesis successfully.